In 1969, two men at Bell Labs unleashed a lab experiment that would quietly grow into the invisible backbone of everything from global banks to your phone. Over the next 50 years, a single trunk would split into hundreds of rival branches, some crowned as true Unix, others surviving as renegade Unix likes, fueling courtroom wars and spawning entire industries. But how did a hack on a PDP-7 become an empire shaping the modern world? To trace every twist of the complete Unix family tree, you first need to see where its tangled roots begin. Inside a quiet Bell Labs lab in 1969, Ken Thompson sat at a PDP-7, a computer so modest it lacked even a lowercase alphabet on its teletype. With no grand plan or corporate backing, Thompson began rewriting his space travel game, but quickly found himself building something far more ambitious. He sketched out a primitive file system, a simple shell, and a handful of core utilities. The early Unix kernel took shape, running on just 8 kilobytes of memory and a homemade disk controller. Dennis Ritchie soon joined, and together they refined the system, adding features like hierarchical directories and background processes. By 1971, Unix version 1 was running on the PDP-11, supporting internal Bell projects. But the real leap came in 1973. Ritchie and Thompson rewrote the kernel in C, a new language Ritchie had designed for clarity and portability. And this rewrite made Unix remarkably easy to move from machine to machine, a radical idea at a time when software was usually tied to single hardware types. The system's philosophy was simple: build small programs that do one thing well and connect them using pipes, a concept introduced in version 3. By 1979, version 7 had spread beyond Bell Labs. It shipped with the Bourne shell and a full suite of development tools, and for the first time was licensed to universities and companies around the world. What started as a workaround for hardware limits had become a portable, adaptable foundation. The DNA of these early versions would soon branch into every corner of computing. In 1981, AT&T took its first major step toward commercializing Unix with the release of System 3. This was no longer just a research project or an academic tool, it was a product packaged for outside customers. System 3 pulled together features from previous internal branches, including version 7, the programmer's workbench, and the Unix TS line. For the first time, Unix was sold as a unified, supported system, ready for businesses and universities to deploy on their own hardware. Just 2 years later, System 5 arrived. In 1983, it set a new standard for what commercial Unix would mean. System 5 Release 1 introduced features like the VI editor and inter-process communication borrowed from earlier Bell Labs projects. The goal was clear: bring order to the growing chaos of Unix variants and provide a stable base for vendors to build on. The evolution continued quickly. System 5 Release 2 in 1984 brought the first official System 5 interface definition called SVYD, a published specification that vendors could follow to ensure compatibility. Release 3, arriving in 1987, added streams for modular networking and remote file sharing, making Unix more flexible for enterprise use. By 1990, the Unix landscape was crowded with competing systems, each with its own quirks. AT&T and Sun Microsystems joined forces to produce System 5 Release 4 called SVR4. This was a watershed moment. SVR4 merged the best elements of System 5, BSD, Sun OS, and even Xenix, creating a single unified platform. For the first time, Unix ran seamlessly across mainframes, workstations, and the new generation of Intel-based PCS. With SVR4, Unix had moved beyond its Bell Labs roots and become the backbone for a new era of commercial computing. Before diving deeper into the branches of the Unix family, it helps to clarify a few key terms that will come up again and again. At the heart of any Unix or Unix-like system is the kernel. This is the core program that manages hardware resources, schedules processes, and handles memory. Everything else, commands, shells, utilities, lives, and what is called userland, sitting on top of the kernel and providing the tools people actually interact with. In many systems, userland includes the familiar command line environment, compilers, networking tools, and much more. The word distribution or distro refers to a complete package, a kernel bundled together with a curated collection of userland tools, configuration files, and sometimes a graphical interface. Each distribution makes its own choices about which software to include and how to put it together, which is why Linux, BSD, and even commercial Unix systems can feel so different in practice. Not every system that looks like Unix is officially recognized as such. The Unix name is a registered trademark now managed by the Open Group. To carry this label, a system must pass rigorous tests for compatibility with the single Unix specification, a set of standards derived from POSIX, which defines how software should behave to be portable across different Unix systems. Only a handful of operating systems earn this certification, including AIX, HPUX, Solaris, and Mac OS. Many others are called Unix-like. They follow the same design principles, often provide similar commands and application programming interfaces, and can run much of the same software, but they do not hold the trademark. Linux distributions and the BSD family fall into this category. Throughout the story, these distinctions will help make sense of the many names and branches on the Unix family tree. By the early 1990s, the Unix world faced a dilemma. Competing systems from different vendors claimed compatibility, but subtle differences in commands, libraries, and even file paths made reliable software development a headache. And in 1993, the Unix trademark moved under the care of the Open Group, a consortium tasked with enforcing a single clear definition of what it meant to be Unix. From that point, only systems passing a rigorous audit verifying every detail against the single Unix specification could carry the official Unix name and logo. A certification demanded more than just passing a checklist. Vendors submitted their systems to a battery of conformance tests covering everything from the C API to file system behavior and networking. The process included source code reviews and binary compatibility checks, ensuring that applications built for one certified Unix would run unmodified on another. The Open Group's audit process became the gatekeeper, holding vendors to a common ABI and API foundation. This move ended years of fragmentation, allowing software vendors and enterprise customers to trust that Unix meant the same thing everywhere. The result was a unified ecosystem with AIX, HPUX, Solaris, and a handful of others standing as true certified Unix systems. IBM entered the Unix market in 1986 with AIX, a system engineered to run on its powerful mainframes and later the RISC-based power systems. AIX stood out for its focus on reliability, availability, and serviceability, qualities enterprise clients demanded. Features like logical partitioning, known as LPARS, allowed a single physical server to act as multiple independent systems, each with its own resources and operating environment. This made it possible to consolidate workloads and increase efficiency, all while maintaining strict isolation. High availability clusters and dynamic system reconfiguration became standard, minimizing downtime for critical applications. HPUX arrived even earlier in 1982, tailored for HP's proprietary PARISC architecture and later Itanium hardware. HPUX introduced trusted partitions, giving administrators fine-grained control over security and resource allocation. The system offered robust support for mission-critical workloads, with features like Process Resource Manager and integrated virtualization tools. Both AIX and HPUX underwent rigorous certification, ensuring they met the single Unix specification and delivered a consistent experience for enterprise customers. Their engineering teams prioritized stability and predictability, making these systems a mainstay in industries where uptime and data integrity are non-negotiable. While their approaches differed, both vendors set benchmarks for what certified Unix could deliver at scale. Sun Microsystems approached Unix not just as a platform to support, but as a canvas for engineering ambition. In 1992, Solaris replaced Sun OS, blending the reliability of System V Release 4 with Sun's appetite for bold features. The company culture encouraged risk and experimentation, and by 2005, Solaris unveiled two technologies that would ripple through the entire industry. ZFS, introduced that year, reimagined how data could be stored and protected. Instead of managing disks and volumes separately, ZFS treated all storage as a single pool. Administrators could create instant snapshots with a single command, ZFS Snapshot Tank Home at Now, and roll back changes or clone entire file systems in seconds. Every block was checksummed, catching silent corruption before it could spread. And this approach made ZFS a favorite for anyone who valued data integrity, from universities to global banks. Trace arrived alongside ZFS, offering something Unix had never delivered before: real-time, zero-overhead tracing of both kernel and user processes. With a probe such as dtrace-n syscall : entry, engineers could watch every system call live, diagnosing elusive bugs or performance bottlenecks without stopping production systems. These inventions were not just technical showpieces, they became the backbone of modern observability and storage, later adopted by FreeBSD, Mac OS, and even Linux. Solaris proved that certified Unix systems could still push boundaries, setting the stage for new debates about openness and ownership in the years ahead. Unixware and OpenServer came from a different corner of the Unix world, built to serve small and mid-sized businesses that needed reliability without the scale of mainframes. SCO, the company behind these systems, had a long history with Unix, licensing code as early as the 1980s, and eventually acquiring the rights to both Unixware and OpenServer. But in 2003, SCO took an unexpected turn. The company filed a lawsuit against IBM, claiming that IBM had contributed proprietary Unix code to the Linux kernel. The case sent shockwaves through the industry, raising fears that the legal status of Linux and open source Unix-like systems was suddenly in question. The lawsuit dragged on for years, with courtrooms sifting through decades of source code and licensing agreements. By 2007, a federal judge ruled that SCO did not actually own the copyrights it was suing over. Those belonged to Novell. The decision undercut SCO's claims, and after a string of legal defeats, the company filed for bankruptcy in 2010. The saga became a cautionary tale about software ownership, intellectual property, and the risks of muddying the historical record. For many, the SCO case reinforced the importance of open standards and clear licensing, a lesson that would shape the next generation of Unix and Unix-like systems. And in the early 1980s, a new force began to shape the future of networking, one that did not come from a corporate boardroom or a government contract, but from the corridors of the University of California, Berkeley. Bill Joy, a graduate student with a knack for marathon coding sessions, took on the challenge of building a robust, portable networking stack for Unix. The result was the Berkeley Sockets API, first released in 4.2 BSD in 1983. This was not just a technical footnote. For the first time, Unix systems had a standard way to communicate across networks, regardless of hardware or vendor. Joy's approach was simple: make networking a core part of the operating system, not an afterthought. He wrote much of the code himself, often working late into the night. The sockets interface he created gave programmers a flexible, universal way to send and receive data over any protocol, TCP, UDP, or even raw IP packets. This model was so effective that it became the foundation for internet software development worldwide. Before this, networking on Unix was a patchwork of vendor-specific hacks and incompatible drivers. Berkeley's implementation changed that overnight. The 4.2 BSD release shipped with a full TCP IP stack, the same protocols that powered the early ARPANET, and would soon define the modern internet. Suddenly, anyone with a Unix machine could connect to the growing global network, run email servers, and experiment with remote logins. The impact rippled far beyond academia. Sun Microsystems, DEC, and dozens of other companies adopted BSD networking code wholesale, baking it into their own systems. The Sockets API became the lingua franca of network programming, copied into Windows, Linux, and nearly every modern operating system. Bill Joy's work at Berkeley did not just give Unix a networking backbone, it set the standard for how computers talk to each other. By the end of the decade, BSD's influence could be seen everywhere. Even as new BSD variants began to branch off, FreeBSD, NetBSD, and OpenBSD, the DNA of Joy's TCP IP stack and the Sockets API remained at the core. The internet's explosive growth in the 1990s and beyond would have been unthinkable without this leap. What started as a student project in a university lab became the invisible thread connecting servers, desktops, and devices across the world. FreeBSD, OpenBSD, NetBSD, and Dragonfly BSD stand as the living proof that the Berkeley spirit never faded. Each of these modern BSDs took root in the early 1990s, after legal battles over proprietary code had cleared the way for open, community-driven development. FreeBSD, first released in 1993, quickly became known for its focus on performance and reliability. It introduced powerful features like jails, a lightweight form of operating system-level virtualization. With a single command, administrators could isolate applications or entire user environments years before the arrival of Docker or Linux containers. This native isolation made FreeBSD a favorite for hosting providers and security-conscious organizations. OpenBSD arrived in 1995, led by Theo de Rat and a team determined to place security above all else. Every line of code is audited, every release is locked down by default. OpenBSD gave the world the PF packet filter, a firewall engine that set new standards for simplicity and power. Commands like pfctl, option F, etc., pf.conf let administrators reload firewall rules instantly, while the system's default stance is to deny unless explicitly allowed. The project's mantra, secure by default, is more than a slogan. It is a design principle enforced with every commit. NetBSD, also born in 1993, took a different path. Its developers aimed for maximum portability, determined to make the system run on everything from high-end servers to handheld devices and ancient workstations. The result is a code base that boots on more than 50 hardware platforms. From ARM to VAX, the motto, "Of course it runs NetBSD," became a point of pride and a challenge to anyone who doubted the system's reach. Dragonfly BSD, launched in 2003 by Matthew Dillon, split from FreeBSD to experiment with new approaches to scalability and file system design. Its Hammer file system offered modern snapshotting and integrity features, while the kernel architecture explored lightweight kernel threads and message passing. These BSDs share more than just code. They reflect a philosophy of careful engineering and open collaboration. Community contributors, students, hobbyists, and seasoned professionals review changes, fix bugs, and propose new features in public. The permissive BSD license allows anyone to build on their work, which is why pieces of BSD show up everywhere, in macOS, in network routers, and even inside Windows. What sets these systems apart is not just their technical achievements, but the way they quietly shaped the world's infrastructure. Jails and PF anticipated the rise of containers and cloud security. NetBSD's portability proved that a single code base can span decades of hardware. The BSDs remain vital, not as relics, but as living laboratories for the ideas that will power the next generation of computing. In August 1991, a 21-year-old computer science student in Helsinki posted to the comp.os.minix news group. Linus Torvalds, frustrated by the limitations of Minix, a teaching system built by Andrew Tannenbaum, announced he was working on a free operating system kernel as a hobby for 386 hardware. His first message was modest. It said, "I am doing an operating system for 386 AT clones." The code, version 0.01, was little more than a bootable kernel that could run Bash and GCC. But Torvalds' timing was perfect. The world was hungry for a free, modifiable Unix-like system that could run on affordable personal computers. Unlike proprietary Unix systems or the BSDs with their legal baggage, Torvalds released Linux under the GNU General Public License. The GPL was more than a legal document. It was a statement. Anyone could use, modify, and share the code, but any changes had to be shared back with the community. This copyleft approach stood in sharp contrast to the permissive BSD license or guarded commercial Unix contracts. The GPL fueled a new kind of collaboration where improvements and bug fixes flowed back upstream, creating a feedback loop that would accelerate Linux's development. The story began on the comp.os.minix threads, where Torvalds and Tannenbaum debated monolithic versus microkernel design. And Tannenbaum argued that monolithic kernels were outdated, but Torvalds insisted that performance and simplicity mattered more for real users. The debate spilled into the global community, drawing in hobbyists, students, and eventually professional programmers from every corner of the globe. Within months, patches and drivers poured in. By the end of 1991, Linux could boot, run a shell, and compile itself on hardware that cost a fraction of what workstations demanded. Linux was never certified Unix, it did not carry the trademark, and it did not follow any vendor's playbook. But the GPL and Torvalds' open, pragmatic approach created an ecosystem where experimentation thrived. The kernel became the heart of a new kind of operating system family, one that would soon be packaged, distributed, and remixed in ways the original Unix architects never imagined. Linux distributions are less a single lineage and more a sprawling forest, each branch shaped by its own philosophy, community, and technical decisions. At the heart of this diversity lie a handful of major families, each defined as much by its package management system as by its user base or release model. Debian, launched in 1993 by Ian Murdoch, set out to build a truly open, community-driven operating system. Its package manager, apt, became a model of simplicity and reliability, letting users install, upgrade, and remove software with a single command. And today, Debian's descendants like Ubuntu, Linux Mint, and Kali run on desktops, servers, and even tiny devices, all bound together by the .deb package format and a vast curated software repository. Red Hat, founded in 1994, took a different approach. It focused on enterprise needs, introducing the RPM package format and a suite of tools for managing complex systems at scale. Red Hat Enterprise Linux, or RHEL, debuted in 2000 and quickly became the standard in data centers and cloud platforms. Fedora and CentOS, both closely linked to Red Hat, offer faster updates and free access to the same core technology. The RPM family now includes dozens of distributions, from OpenSUSE to Oracle Linux, each offering its own take on stability, support, and innovation. SUSE, which began in Germany in 1992, built on the RPM format but carved out its own identity with tools like YAST for system configuration and a focus on enterprise reliability. OpenSUSE, its community-driven sibling, became a playground for experimentation and rolling releases. Arch Linux, First released in 2002, took the opposite path, minimalism and user control above all. Its Pacman package manager is fast, lightweight, and expects users to know what they want. Arch's philosophy inspired a wave of derivatives, including Manjaro and Endeavor OS, that aim to make its power more accessible. Each of these families supports a constellation of specialized distributions, from security-focused systems to multimedia studios and scientific platforms. The choice of package manager, apt, RPM, or Pacman often defines the user experience as much as the desktop environment or kernel version. This organizational flexibility is what gives Linux its reach, making it possible for anyone to find or build a system tailored to their needs. Linux's rise from a hobbyist project to the backbone of global infrastructure owes as much to its technical flexibility as to the communities that rallied around it. The real breakthrough came with the introduction of new kernel features, namespaces, and control groups, also called C groups, which first appeared in the 2.6 series. These features gave administrators a way to isolate processes, networks, and file systems, and to control how much CPU, memory, or disk any group of processes could use. What began as a way to keep one user's runaway process from taking down a server quietly unlocked a new world of possibilities. By 2013, these building blocks came together in an unexpected way. Docker launched as an open source project, offering an easy way to package applications and their dependencies into lightweight containers. With a single command, Docker run hello world, developers could spin up isolated environments in seconds on any Linux machine. Containers did not just make deployment faster, they made it possible to run thousands of applications on a single server, each in its own sandbox, with near zero overhead. This approach changed the economics of computing. Instead of running one application per machine, companies could pack their infrastructure densely, scaling up or down as needed. Cloud providers embraced containers, and Linux became the default platform for massive data centers. Today, over 80% of cloud servers run some form of Linux, and nearly every major cloud service is built on top of these container primitives. And the kernel community's relentless pace, thousands of contributors, rapid releases, and a culture of peer review meant that Linux could quickly adapt to new hardware and emerging needs. The diversity of distributions, once seen as a weakness, became a strength in the age of containers. Whether running Ubuntu, Red Hat, or Alpine, the same container could launch anywhere, making Linux the universal engine of the modern cloud. When Apple launched Mac OS X in 2001, it quietly introduced a certified Unix core to millions of everyday users. Underneath the familiar desktop sits Darwin, an open source foundation powered by the X and U kernel, a blend of Mach microkernel technology and BSD subsystems. This hybrid design brings together the flexibility of Mach, handling memory and multitasking, with the stability and networking strength of BSD inherited from decades of open source development. The result is a system that feels polished and approachable, but remains grounded in the same Unix principles that shape servers and mainframes. Apple's engineers did not just copy BSD. They layered their own innovations, like the Aqua interface and advanced graphics, over a robust POSIX environment. This combination allowed Mac OS X to support a full suite of Unix command line tools right out of the box, making it a favorite among developers and power users. In 2007, Apple earned the Unix 03 certification from the Open Group, joining the ranks of AIX, HPUX, and Solaris. This was not just a badge. It meant that Mac OS passed strict tests for compatibility, reliability, and standards compliance. The same Darwin core powers iOS, iPadOS, watchOS, and tvOS, extending certified Unix roots to mobile devices and beyond. While the user interface remains tightly controlled and proprietary, the open source Darwin layer is available for anyone to inspect or build upon. This unique blend of open foundations and polished experience sets Apple's Unix lineage apart, bridging the gap between consumer design and enterprise-grade reliability. Android's arrival in 2008 changed the shape of mobile computing almost overnight. Built on a modified Linux kernel, Android offered hardware makers a free, flexible foundation for everything from flagship smartphones to budget devices. Google's engineers stripped down the kernel, added a custom userland, and introduced a new runtime called ART to manage apps efficiently on limited hardware. And the result was a system that could power touchscreens, cameras, and sensors with the reliability and multitasking Linux was known for. And within a few years, Android claimed a majority share of the global smartphone market. Today, it runs on billions of phones, tablets, smartwatches, and even televisions, quietly making Linux the most widely used operating system on the planet. Chromios followed in 2009, bringing Linux to a new class of lightweight laptops. Instead of installing traditional desktop software, users worked almost entirely in a web browser. Chromio started with a Gentoo-based Linux kernel, then layered in tight integration with Google services and automatic updates. Later, the Crostini project added full Linux containers, letting users run desktop Linux apps alongside web tools. This blend of cloud-first simplicity and kernel-level flexibility made Chromebooks a favorite in schools and businesses. Both Android and Chrome OS show how the Linux kernel adapts far beyond servers. Its modular design lets companies build for touchscreens, keyboards, or even voice controls while keeping security and performance at the core. And the same open source foundation now powers everything from smart speakers to cars, revealing just how far the Unix family tree has branched into daily life. Outside the spotlight of major vendors and mainstream distributions, a handful of operating systems have pushed Unix ideas in unexpected directions. Minix, first released in 1987 by Andrew Tannenbaum, was designed for teaching, not production. Its microkernel architecture split the core into small, isolated services, making it easy to study and modify. Though it never saw wide commercial use, Minix became a proving ground for new concepts and famously inspired Linus Torvalds to start Linux after finding its limitations too restrictive. QNX arrived even earlier, in 1982, targeting real-time control systems where timing and reliability matter more than raw speed. Built from the ground up as a microkernel, QNX could guarantee that critical tasks like managing factory robots or medical devices would run on schedule every time. Its modular design allowed developers to assemble only the pieces needed for a given job, making it a favorite for embedded hardware and automotive systems. Plan 9, launched by Bell Labs in 1992, set out to rethink the very meaning of an operating system. Its designers imagined a world where every resource, files, devices, even network connections could be accessed through a unified, distributed namespace. Plan 9's influence shows up in everything from container file systems to modern cloud infrastructure, even if the system itself remains a research curiosity. Together, these niche operating systems show how the Unix tradition continues to spark experimentation, curiosity, and the search for new ways to organize the digital world. Nearly half of all servers worldwide still run Unix or Unix-like systems, shaping how billions experience technology every day. As open standards and interoperability define the next era, the choices set in motion by Unix's branching legacy continue to ripple through every digital device. The code may evolve, but the philosophy endures, quietly scripting the world's future. How we build on that foundation will decide what comes next. Thanks for watching. Share your thoughts below.